One of the most basic things that you can do with Python is to use it to evaluate simple mathematical formulas, just like you would with a handheld calculator. So let's learn how to do that. We'll take the example of a tennis ball launcher that launches tennis balls at a speed v naught or v sub 0 and angle theta naught. And it does that from a height of 80 centimeters off the ground. That's h. And we would like to choose v naught and theta naught such that the first bounce of the ball occurs at 10 meters from the launch point. That's d. So to find or to solve this problem, we're going to make a simplifying assumption that there's no air resistance and that the ball is only affected by gravity. And in this case, it follows the trajectory of a parabola, which is this dotted gray line. So if you apply Newton's laws to the ball, you will find a formula for the trajectory, the parabolic trajectory, in terms of h, theta naught, and v naught, and the constant g of gravity. And that formula is right here. Y here is the height of the ball from the ground. So you see y measures the height from the ground, and x measures the distance traveled horizontally from the launch point. So this formula you can see when x is equal to 0, y is equal to h, and it is a quadratic or a parabola in x. So we can plug the condition that it bounces at 10 meters, that is y is equal to 0 when x is equal to 10 meters. And then we're going to also assume that, well, let's say theta naught is fixed. Just to simplify, theta naught is, for example, equal to 45 degrees. Then our only unknown is v0. And we can isolate it from this formula, and we get this formula below for v naught. Okay, well, now we have to use Python to evaluate this formula. Okay, so here's a Jupyter notebook that is mostly empty except for this image here that reminds us of the formula. And I like to begin by defining all of the constants that are involved. So we have g, the acceleration of gravity, d, the distance to bounce, theta naught, the initial angle, and h, the height above ground. So let's define those. So g is 9.81 meters per second squared. And we don't include the meters per second squared in the code, but it is a good idea to add a comment that reminds us of what this g is. So in Python, we use the hash symbol for comments. So I put a hash, and then I can say gravity or acceleration of gravity in meters per second squared. And what this symbol does is that it tells the interpreter to ignore everything that comes after it. Then d is 10. That is the distance to bounce in meters. Then we have theta naught. We said it was going to be 45 degrees. That is, the initial angle in degrees. And finally, we have h, which was 80 centimeters, which we can just say is 0.8 meters, just to have everything in the same units. So this is initial height in meters. Okay, now that we have all of the constants defined, we can proceed to evaluate the expression. And this is a pretty complicated expression. It involves trigonometry, the cosine and tangent. It has exponentials, cosine squared and d squared, and it also has a square root. So we're going to need some of the components of the math package of the standard library. And to use the math package, we need to import it. So to do that, we use the import statement. We say import math, and upon evaluating that line, it's going to import all of the functionality of the math package into our workspace. So let's see what is in this math package. The math package includes many functions, and I'm not showing them all here. Here I'm just showing the ones that we need the most. Things like trigonometric functions, exponential functions, and also some constants like pi, 3.1415, etc. Euler's constant, inf stands for infinity, and nan stands for not a number. So these two, inf and nan, are constants that you can use as placeholders to indicate those values, inf and not a number. Then we have the standard trigonometric functions, cosine, sine, tangent. These two, radians and degrees, are for translating between radians and degree units of an angle. And then we have the standard inverse trigonometric functions like the arccosine, arcsine, arctangent. And then atan2 is a signed version of the arctangent, where you give it the numerator and the denominator, x and y, and it distinguishes between angles in, say, the first and third quadrant or the second and fourth quadrant. And then we have exponential functions. exp is e to the x. exp2 is 2 to the x. Log is the logarithm, and you take the logarithm of x, and you can supply a base for that logarithm. And if you don't supply the base, it's optional. It will just return the natural logarithm, so the base log base e. Then we have log base 2 of x, log base 10 of x. POW stands for power, so this is x to the y. And then we have square root of x and cube root of x. So let's try some of these. To use one of these components of the math package, we need to prefix that thing with math dot. So for example, if we wanted the constant pi, we'd say math dot pi and evaluate that. There you have it. Here's e, math dot e. Let's see, the cosine, that's a function. So we have to open close parentheses, and we're going to pass the argument of that cosine in through the parenthesis. So we're going to need the cosine of theta. So that would be cosine theta naught. However, this is in degrees, 45 degrees, and these trigonometric functions require that you pass in the argument in radians. So we need to translate theta naught into radians, and we do that with the math.radians function. Okay, so now we have theta naught in radians, and we get the cosine at 0.707 as expected, square root of 2 over 2. Okay, let's try the exponential function. exp, that's e to the 1, that's just e. That would be the same as evaluating just e. Okay, so, but exp2 would be e squared. exp negative 2 would be 1 over e squared. The logarithm, if I say the logarithm of 2, that would be the natural logarithm of 2. And if I wanted, say, the base logarithm, the base 10 logarithm of 2, I could pass in the base as a 10. And that would be equivalent to using the base 10 logarithm function. What if I wanted the base 10 logarithm of 10? That's obviously 1. This is the base 2 logarithm. Okay. If I wanted, say, to evaluate 10 to the 4, that's that. If I wanted to evaluate 3.54 to the 4, I can use this power function. Okay, so the math package is going to give us the cosine, the tangent, and the square root. We still need to multiply and divide things. And that is made possible by simple scalar arithmetic operations in Python. So this table shows the scalar arithmetic operations that are available. We have addition, subtraction, multiplication is an asterisk, division is a slash, exponentiation, which is the same as this power function from the math library, is a double asterisk. The quotient is a double slash, and the modulus is a percentage sign. Now, if you don't know what these are, the quotient is the integer part of a division, whereas the modulus is the remainder of a division. Let's see an example of these. So this part does not require the math library to have been imported. We could, if we wanted to evaluate 3 cubed, that would be like that using exponentiation, or 3 squared, or it could be 3.4 to the 2.6 with exponentiation. How about the quotient? 8, well, let's take division first. 8 divided by 3, that is 2.66. And if we only wanted to keep the 2 part, all we have to do is take the quotient, and that just keeps the integer part of a division. And if we only wanted to keep the remainder, 8 divided by 3 is 2.66, so we have an integer part of 2 and a remainder of 2. So we could get that by using the modulus. 8 modulus 3 is 2, but 8 modulus 2 is going to be 0 because 8 divides 2 exactly. Okay, so now we have everything we need. Let's go ahead and evaluate the expression. So we have v0 is equal to square root. So math dot square root of open close parentheses. And inside here, we're going to put this fraction. The fraction has as its numerator gd squared. So we can do that with g times d squared. Now, at this point, there's a little bit of an ambiguity because we don't know whether Python is going to evaluate g times d squared as desired, or it could evaluate this, g times d squared, depending on whether it first does the multiplication operation and then the exponentiation, or if it first does the exponentiation and then the multiplication. So this has to do with the order in which Python executes the operations in an expression, and we'll talk later about how the order of operations works. As it will turn out, this will be correct because exponentiation comes before multiplication. But if you are ever in doubt and you want to make sure, just add parentheses, and parentheses will ensure that the operation that you want to happen first happens first. So in this case, we do this, then divide. I'm going to put parentheses to enclose the entire denominator here. And the denominator has 2 times, and then cosine squared. So we have math.cosine and theta naught. But as you'll recall, this has to be in radians. And since I'm going to use it twice, theta naught here and theta naught here, I am going to define a new variable called theta naught r, which is just the theta naught in the unit of radians. And then I can use this theta naught r and plug it into the cosine. That just makes things a little bit more compact. And then this cosine has to be squared. Okay, and now I'm going to multiply it by this term. And so that's going to be in parentheses. And that term has h plus d times the tangent of theta naught r. Okay, so let's see. Do I have everything? It looks like this parentheses closes here, this one closes here, and this is the final one that closes the square root. So ready to evaluate? Here we go. And that worked well. Okay, but it doesn't print the value of v naught. So just as a final tip, when you want to print a value from a Jupyter Notebook cell, well, you can use the print function as always, print v naught, and that will give me the value of the velocity. In this case, 9.53 meters per second is the speed at which the tennis ball should be launched so that it bounces 10 meters away. But it's also not necessary. So Jupyter Notebooks will, by default, print the last row of each cell. So you can remove this this call to the print function, and the result is the same. But if we removed this, as we had before, now the last row is this assignment row where it assigns a number, which is the right-hand side, to a variable name, which is the left-hand side, and printing that doesn't print anything. So that's why we put V0 here, and it gives us the value of V0. Okay, so that is evaluating mathematical formulas with Python. Many mathematical formulas to evaluate out there. I hope you enjoy, and I will see you in the next video. Bye-bye.